So limits. These are like the fundamental basic building blocks of calculus. Like all of calculus is defined based off of limit definitions. So it's a huge topic, and it's the very first thing that we'll actually cover again in calculus next year. But let's start off with the basic super informal definition. A limit is defined as the intended height of a function. So what that basically means is if we're kind of looking at a graph and we were to say like, hey, like what's the height right here, whatever that is, that's the limit at that value. And it gets a little bit trickier, potentially maybe when we don't have a value there, and that's where this intended height comes into play, is that it doesn't matter if the height's not there, the limit will say that the intended height should have been there. So let's just take a look at these two examples real quick. I have the limit as x approaches 2, so that's how we refer to this, limit as x approaches 2 of x squared. And what I want to do is just first find where x equals 2 is, so that's right here, and that would be way up here with a y value of 4. So what this says right here officially is as we get closer and closer to an x value of 2, it doesn't matter which direction we're coming from, the y values are getting closer and closer to a height of 4. So that's what this limit is going to equal. The limit as x approaches 2 of x squared is going to equal 4 because it looks like it's supposed to be reaching this height of 4. So that's going to be the answer for the first one. Next one's a little bit trickier. So first, how does this end up like this? What we really want to do is factor the top. So if we simplified the equation here, we would get x minus 2, x minus 4 over x minus 2. That cancels. We know that that creates a hole at the x value of 2, and if we want to figure out what the y value is of that hole, we plug it in here. We get 2 minus 4, that's going to be negative 2. So we know that the coordinates of this hole are actually 2, negative 2. Okay? So when this says the limit as x approaches 2 of this function, we're saying, hey, as we get closer and closer to this x value of 2, that's right here, what is the y value getting closer and closer to? And the y value is getting closer and closer to negative 2. It doesn't matter that it never reaches it. The limit of this function is going to be negative 2 as x approaches 2 because it looks like it's supposed to reach it, even if it doesn't. Okay, next we have this concept of left and right side limits. So I have this graph of a function here, f of x. It's a piecewise function. It has a break in the graph right here. So when we're talking about left and right hand side limits, what we're really mentioning is basically if we come from above, so from the positive side of a number, or we come from the negative side. So the way we denote this is with this little plus sign up here that looks like it's an exponent. This means from the right, okay? So we would read this as the limit as x approaches 4 from the right of f of x. This one is going to be from the left, same idea. So let's look at this. If we approach 4, which is right here, so I'm just going to put a big dotted line that represents where 4 is. As we approach this value from the right, so I'm going to trace the function from the right-hand side, I'm approaching this height right here. So from the right-hand side, it looks like this function is reaching a height of 2. Now if I approach it from the left-hand side, so that's me coming across here, it looks like it's approaching a height of 1. Okay? Now, down here we have this, which I just refer to always as the actual limit, but this is the limit from both sides if it doesn't have the little plus or minus. And the only way this exists is if these are the same. So if I look at this from the left-hand side and the right-hand side, they must be equal in order for the limit to exist. And since these do not, as Lindsay Lohan taught us in Mean Girls, the limit does not exist. Now it's important to note here that f of 4 does exist. F of 4 equals 1 because that's where the point is filled in. So we have the limit from the right is 2, the limit from the left is 1. The actual limit does not exist because these are not the same thing, and the function itself exists at 1. So this is something that I'll be asking frequently, and you'll be asked next year in calculus, is to basically evaluate all 4 of these different things. The limit from the right, left, the actual limit, and what the actual function's doing there. So evaluating limits graphically is very easy as long as you have the graph. So I'm going to look here, we're doing as x approaches -5 from the left, the right, the actual limit, and then what the function actually equals at -5. So what I'm going to do is just, and this is just for this one, I won't do this for other ones probably, but I'm just going to put a little dotted line where -5 is, so I know that this is the x value that I'm focusing on. And when I'm going from the left-hand side, that's as I'm going like this towards that line. Okay, so as I'm moving from the left side closer to this line, following the function. Same thing, the right-hand side, as I am moving towards that value. So the limits of these are basically just asking me, what are they approaching? So this blue one, it's approaching this height of 1. So that's what this limit is. From the left-hand side of -5, the function looks like it's supposed to reach a height of 1. From the right-hand side, the function looks like it's supposed to reach a height of 5. Okay, these are not the same number, so the limit does not exist. That doesn't mean the function doesn't exist. The function does exist. We have a point right there at 1. So f of -5 is actually equal to 1. So let's look at a couple others. For 0, as we approach from the left, that's coming this way. It looks like we're supposed to reach a height of 1. It doesn't matter that there's a hole there. If we come from the right-hand side, same thing. It looks like we're supposed to reach a height of 1. So since left and right are equal, that tells us that the real limit is also equal to 1. Now they ask us what's going on at 0 with the function, and there is nothing defined there. There's a hole. So this is undefined, which is different than does not exist. Subtle, but let's not get into it. At 2, we have this little line here indicating a vertical asymptote. As we approach from the left-hand side, it's going up towards positive infinity. From the right-hand side, it's going up towards positive infinity, and that means that we will say that the real limit is approaching positive infinity, and at 2 it is undefined because that vertical asymptotes were undefined. Now there is this kind of tiny little note that we need to maybe mention over here, which is that technically infinity is actually a does not exist because we can't actually reach infinity. It's not a number that's reachable. So technically when we write infinity over here, they are actually does not exist because we can't reach a height of infinity, and limits are intended heights. But it's very useful for us to know that it's not just that it doesn't exist because the left and the right side are different, and that it doesn't exist because it's infinity. So basically all math people kind of came to this agreement that even though it doesn't exist technically, it's much more useful for us to just write infinity or negative infinity when we have a limit doing that. And we'll focus more on that in the next lesson. For 6, as I approach from the left-hand side, that's going to be down at -1. The right-hand side is going to be up at 3, I believe. Those are not the same number, so this does not exist. It has the point up here at 3. So f of 6 is 3. When I go towards negative infinity, okay, so that's over here, this graph looks like it's approaching a height of -3. That's what this little dotted line is supposed to be telling us. And on this side, it's going up forever. So I'm going to say positive infinity. And there you have it. You just have to look at it and see what the left and the right-hand sides are, and that helps you fill out everything in this entire problem. Sketching a graph from given limits tends to be the hardest part for a lot of people. So what we're going to do is group these things together. So everything that has to do with the x value of 1, we're going to group together. And we're just going to do this in pieces. And we always start with the point that they gave us. So if I'm looking at these things, f of 1 equals 2. So I'm going to find f of 1, and I'm going to put a solid point here at 2. Okay, so I know that that's true. Next, if I look at this, I'll start from the left-hand side. So from the left-hand side, as we approach 1, we're going to be reaching this height of 2. So what I'm going to do is just put a little tail here on the left-hand side only. Now the next one says from the right-hand side, we're approaching a height of 3. So that's up here. And I know that at 1, I can't actually equal a height of 3. So I'm going to put an open circle and put a tail on the right-hand side. Now the other part here, they said that the limit does not exist. We didn't really need that because the left and the right aren't equal. The left equals 2, the right equals 3. So these little tails are just showing us the left and the right. So that's what we're going to do for the limit as x approaches 1. We'll kind of fill things in later with it. Next, I will look at the limit as x approaches 4 equals 5, but f of 4 equals 1. So I'm going to come over here, f of 4 equals 1. I will fill that in. Now, The limit as x approaches 4 equals 5. Okay, so that means that from both the left and the right, it's approaching a height of 5, which is way up here. But I know that it can't actually equal 5 because we already know it equals 1. So I'll just put a little tail from left and right to signify that that's happening on both the left and the right-hand side of x equals 4. Next, we have these two limits. As x approaches infinity, we're going down, and as x approaches negative infinity, we're going up. So I'm just going to, way over here at the end of the graph, put an arrow going down, and way over here I'll put an arrow going up. So this is as x goes towards positive infinity, it's down, x goes towards negative infinity, it's up. Last thing I need to do is just connect the points, basically. So I'll always start from the left and work my way forward. So from here, the next tail that's closest to me is this green one right here, so I will just connect these. And it doesn't really matter what this looks like as long as it maintains being a function. Now, if I follow the green all the way through, that's going to end right here, and I just need to go to the next tail, which is up there. I follow this through all the way to the end of its last tail, and then it connects to the next one way down here. So I just have this point floating there. That's perfectly fine. It doesn't break any rules whatsoever. And this is going to be a rough approximation of the graph given that information. All right, so to evaluate limits numerically, we basically just make a table of values, which I've already provided for you for this case, and then we just look at what's happening as we get closer to the number we're caring about. So if we're looking at 4 from the left-hand side, the x values here are getting closer and closer to 4, coming from below 4. And if we look at it, the y values are 7.9, 7.94, 7.993. So it certainly looks like when we're coming from this left-hand side that it's approaching 8. Now, when we look at 4 from above, so this is when we start greater than 4 and we're getting closer and closer to 4, the y values here, again, look like they're converging on 8. So we would 100% expect that the intended height of this function would be 8. From both the left and the right, that gives us the real limit over here. When we look at this next one, as we approach negative 2 from the left, it looks like the y values are approaching 3, negative 3. If we look at them from the right-hand side, these y values are getting closer and closer to 6. These are not the same number, so the actual limit at negative 2 does not exist. This one's a little bit tricky to see numerically anyway, but if we look at the numbers, they're getting greater, bigger and bigger, or more negative in this case, as we get closer and closer to 0. So I would say that this is going towards negative infinity, and I don't have an infinity symbol in the program I'm in right now, so we have to deal with, that. Same thing from this side. If we're getting closer to 0, the numbers are getting larger and larger, so that I would say is going towards positive infinity. These are not the same number, so the actual limit does not exist. Down here, as we're approaching 4 from the left, it looks like the y values are approaching negative 7. Same thing from the right-hand side. They are getting closer and closer to negative 7. Those are the same number, so the actual limit will be negative 7. For this one, as we approach negative 2 from the left, it looks like the y values are approaching 0. And same thing from the right-hand side, they do look like they're approaching 0 as well. Those are both the same number, so the actual limit is 0. Last but not least for this section, we have 3.8, 3.9, 3.99. So from the left-hand side, it definitely looks like it's approaching 4. And then we have 3.1, 3.05, 3.001. So from this side, it looks like it's approaching 3. Those aren't the same number, so the actual limit does not exist. All right, let's take a look at some of these basic properties of limits. Okay, so b and c are just real numbers, and n is some sort of positive integer, okay? So positive and basically a whole number. So limit as x approaches some number of a constant equals that constant. So that's an easy property. Basically, if you have the limit of a number, it's going to equal that number. 2 is saying the limit as x approaches c of x, that's going to equal c. So this is going to basically be what we're doing in the next section, which is direct substitution, where essentially whatever x is approaching, if we're just looking at it at x, then that's going to be the number. Same thing for 3. It's essentially saying we can do direct substitution if we have x raised to a positive integer, or if we do the nth root, same thing. And with trig, same thing. So that's leading us up to this section down here, which basically says we can direct substitute whatever the value in is that we're approaching, as long as it doesn't violate any domain issues. So one of the easiest ways of evaluating limits is with something called direct substitution, which basically means that as long as the graph is continuous, and we can direct substitute in without getting any sort of domain violations, that actually is what the limit will equal. So for this first one, limit as x approaches 4 of x squared, I can literally just take 4 and plug it in there, so I get 4 squared. So this limit will equal 16. Same thing over here, plug this in, I get 5 times 4. This limit is going to equal 20. Here, plug in pi, so I get tangent of pi over pi. Let's see, tangent of pi is 0, so 0 over pi is 0. Here, direct substitute in, square root of 9 is 3. That's what this limit's going to equal. Direct substitute in pi, so I get pi cosine pi. Let's see, cosine of pi is negative 1, so this is negative pi. Here, direct substitute this in, I'm going to get 3 plus 4 squared, so that's going to be 7 squared, or 49. Plug negative 1 in, I'm going to get 1 minus 6, that's going to be negative 6. Here, plug in same idea, I'm going to get positive 1 minus 6 over negative 1 plus 3, and that's negative 6 over 2, that's negative 3. Now notice, if I had done x approaches negative 3, I could not direct substitute here because that would have given me a 0 in the denominator, which is domain violation, which is what the next exploration is. So this next exploration is to really go over what happens when direct substitution fails. So if I try to direct substitute in 5 right now, I'm going to get 5 minus 5 in the bottom, I'm going to get 0. So that doesn't work. But our first strategy that we can do if direct substitution does not work is to try to factor things to see if we can eliminate what's preventing us from direct substituting. So if I look at this, I can factor the top, it's x minus 5 times x plus 2. So I'm really doing the limit as x approaches 5 of this stuff. And those x minus 5s cancel, so I can really say that this is the limit as x approaches 5 of x plus 2. And now I can direct substitute because there isn't anything that's going to give me 0 in the denominator, so I will get 5 plus 2, or 7. So here we have 4 examples that just go over the 4 main ways of solving limits algebraically. So first is always direct substitution. We always try to direct substitute before we do anything else. So if I direct substitute into here, I will get 0 squared minus 1 over 0 plus 3. So I don't get any domain restrictions, so that means that direct substitution works, and I'm left with negative 1/3. So that's what this limit will equal. Now for factoring over here, if I try to direct substitute 2 in, I get 0 in the bottom. So we'll just try factoring top and bottom. So I'll get x minus 2, x minus 4 over x minus 2. The x minus 2's cancel. I'll now direct substitute into the x minus 4. So I'll get 2 minus 4, which is negative 2. And that was the one that we explored on the first page, actually. For this one, again, we'll try direct substitution. You can technically factor this, but most people don't recognize how to factor it. So we'll just view this as a conjugate method. But if I plug in 16, I get 0 in the bottom. So I'm not allowed to do direct substitution. I will multiply top and bottom by the conjugate. So that's the square root of x plus 4, top and bottom. On top, I'm going to get x minus 16. And here's our first little hint when we're doing this, which is you only want to actually FOIL out the things that are conjugates and leave the other part factored still. So I've done that on the bottom, and that's because I can now cancel. So this is really asking me the limit as x approaches 16 of 1 over the square root of x plus 4, and I can now direct substitute. So basically, our goal here is to eliminate what's preventing us from direct substituting, and once we've done that, then direct substitute. So I'll get 1 over 4 plus 4, or 1/8. Over here, we have fractions and fractions, and if we plug in x equals 2, we get 0 in the bottom. So I'm going to multiply top and bottom by the least common denominator of all the mini fractions. So that's going to be 2x as my least common denominator. So I'll do 2x times each one of those over 2x times each one of these. And again, it's basically going to be the things that have fractions, I'll actually distribute it through, and the ones that don't, I will leave unfactored. So if I do this, 2x times 1 over x is going to be 2. 2x times negative 1/2 is going to be negative x. And on the bottom, I will leave these ones written like that. And now we have this right here. So these guys cancel, but since they're opposites of each other, they cancel to negative 1 instead of positive 1. So I really have the limit as x approaches 2 of negative 1 over 2x. I can now direct substitute 2 in, and I get negative 1/4. Done. Limits aren't that bad.